Hello everyone and welcome back to Nunley Math. I'm Aaron Nunley. Thank you so much for joining us here today for our lesson on solving equations. You may recall that we are in the middle of a unit on algebra for the pre-algebra student, and what we're trying to do is we're trying to examine patterns that arise in elementary school arithmetic that can be generalized to numbers even when we don't know what the number is. We refer to those as variables, and this idea of using generalized patterns is really the foundation of Algebra 1 and all higher level mathematics. Now, in our previous videos, we have talked about four properties in particular that you are going to want to be familiar with in order to understand today's lesson. We talked about the definition of subtraction and how subtraction can be rewritten as adding the opposite. We've talked about the commutative property, where it doesn't matter what order we write the numbers in if all we're doing is adding or multiplying. We talked about the associative property and how if all we have is one long string of addition or one long string of multiplication, we can regroup those numbers any way we want. And we've talked about the distributive property and how if we have this many of a group, that means we have this many of everything in the group. These are just some foundational principles or properties or definitions that we use all the time in Algebra 1. If you're uncomfortable with those ideas, then you probably need to go back and review those lessons prior to watching this video. This video deals exclusively with the property of equality and how we can use the property of equality to solve algebraic equations. And in doing this, I want you to keep this definition in mind. I can do whatever I want in an equation as long as I do it to both sides of the equal sign. It's the property of equality. I can do whatever I want to an equation as long as I do it on both sides of the equal sign. So, more algebraically written, we would say if A equals B, if A and B are the same, then that means I can add something to both sides or subtract something from both sides or multiply it. I can do basically anything I want as long as I do it on both sides of the equal sign. Now, if you are an algebra teacher and you're watching this, yes, I am aware there are certain exceptions to this rule. Those exceptions tend not to arise in a pre-algebra classroom or honestly most of the time in an early Algebra 1 classroom, and we would address those exceptions as they pop up. They're not really terribly relevant for us right now. It's just important for us to remember that this rule almost always applies. For those of you that are learning this for the first time, I want to give you an illustration that may help this make more sense to you. This will be a little bit less mathy. Let's say you have a dollar bill. And let's say I have 4 quarters. Now, we know that even though those look different from one another, they are the same value. 4 quarters makes $1. So if I go to a vending machine and it says something costs $1 and I put in 4 quarters, it will accept that because it has the same value. Likewise, if you have $4 and I want to trade it with you and hand you a dollar bill instead, those are the same. But here's what the property of equality tells us. It says, if these two things have the same value, and I add a quarter to both sides of the equal sign, notice they were, let me go backwards, they were both worth $1. If I put a quarter on both sides, now they're both worth $1.25. And if I add another quarter, now they're worth $1.50. You see, it doesn't matter how much money I add. If I'm adding equal amounts to both sides, then these will always remain equal. Likewise, I could take things away. If I had $1 over here and $1 over here, and I began to subtract things, as long as I subtract the same amount from both sides, I'm always going to have equal amounts. That's the property of equality. So let's say I have an algebraic equation that looks like this. By the way, you'll notice that I'm using the word equation now instead of expression. Up until now, we've not had any equal signs. Once I stick an equal sign in it, I have an equation. This is saying that the expression on the left side and the expression on the right side have the same value. So I have a 2 and a 3, and I have a 5. Those two sides are equal to one another. But suppose I were to add 1 to both sides. Are they still equal? This is now 5 plus 1. This side is a 6, and this side is also a 6. They are still equal to one another. Or let's say I were to go through and multiply both sides by 3 and then add a 1. Are they still equal? 3 times 5 is 15, plus 1 is 16. 3 times 5 is 15, plus 1 is 16. They're still the same. As long as I start with the same thing, and I do the same thing on both sides of my equation, I'm always going to end up with values that are equal to one another. The property of equality allows us to change the way an equation looks without changing the value of the original numbers or the truth of the equation. Okay, property of equality. Let's put that to use. So let's take a look at this. I have an algebraic equation for you. X plus 4 equals 7. I know probably most of you can look at this and say, well, what value of x would make this true? And most of you are going to realize right away that only a 3 would make this true because 3 plus 4 equals 7. I want you to set that aside for just a second because I'm not really interested in what number makes this work. We can all do that with easy mental math. I'm more concerned with thinking through a process that we can use if I gave you more difficult numbers so that you'll be able to solve any of these problems, not just simple easy ones. And I'm going to use the property of equality to do this. The property of equality says I can do whatever I want as long as I do it on both sides of the equation. So I could add 10, I could subtract a 14, I could divide by 7. It doesn't really matter what I do. Those values, or those two sides, are going to stay equal to one another as long as I do the same thing on both sides. And I'm going to show you what I'm going to do. I'm going to pick a minus 4. And I'm going to pick that minus 4 for a very specific reason. Because when I perform this computation, positive or plus 4 subtract 4 is going to give me a 0. I knew this was going to give me a 0 because 4 and negative 4 are additive inverses or opposites. Even though I could do anything I wanted to do, I intentionally picked the additive inverse when adding these together because I wanted this to turn into a 0. Why do I want it to be a 0? Well, because adding 0 doesn't do anything. That's the identity property. Any number added to 0 stays the same. And this gives us a pattern we can use to solve all kinds of single-step equations. No matter what you start with, if it's a single-step equation, we can use the property of equality to try and turn things into easier numbers. And then in this case, because it's a plus 0, I can use the additive identity to show that adding 0 doesn't do anything. Now, what I require my students to do in class is after they've told me what value makes this true, I require them to do a check. They have to write the word check, and they take the original problem that they started with, and they plug in the value they said that should work. In this case, we said 3 should work. Does 3 plus 4 equal 7? Well, if I do the 3 plus 4, my sides match, and I know that I found the right answer. If I do this and my sides don't match or give me a statement that's not true, then I know I've done something wrong and I need to try again. This idea right here is the entire lesson for today. Now we'll try several examples of this. We'll do a few that look slightly different, but this same principle is going to happen over and over again. X minus 11 equals 25. Again, I'm not so much concerned with the answer, which you can probably figure out with a little mental math, as I am with the process that we use to arrive at that answer. So I want you to think about the property of equality. If my goal was to get this x all by itself, I want to get rid of this minus 11. What can I do to both sides that will cause that minus 11 to go away? Hopefully you realized that it was adding 11. Because when I add 11 to both sides and I perform some basic computation, negative 11 and plus 11 make a 0. 25 plus 11 then gives me 36. I wanted to pick this 0, so I chose the additive inverse of 11 in order to get the 0. I like having the 0 because the identity property of addition says adding 0 doesn't do anything. Anything plus 0 is the same. And your answer is 36. The only way this statement is true is if it's a 36 minus 11. Once again, I would check that, rewrite the original problem, plug in the number we said should work, and then just subtract to see if the sides match. If the sides match, we know we did it correctly. If the sides do not match, we know we've done something wrong and we need to try again. Make sense? Here's one. 5x equals negative 40. Suppose I wanted to try and find out what value of x makes this true. Certainly you could do it with some mental math, but we're more interested in the process. If my goal is to get that x by itself, I need to get rid of a times 5. Do you have any ideas how you might be able to get rid of a times 5? Here's what I would do. I would take and multiply both sides by 1/5. Do you know why I would do that? 1/5 times 5 equals 1. Now, negative 40 times 1/5 equals negative 8. You see, I like the fact that this is a 1, and I intentionally picked the multiplicative inverse in order to get that 1. Anything multiplied by its multiplicative inverse will always give you a 1. Why do we want the 1? Well, anything multiplied by 1 stays the same. That's the identity property of multiplication. You have the additive identity, which says adding 0 doesn't change the number. You also have a multiplicative identity that says multiplying by 1 doesn't change the number. Now, this is a little trickier for some people because they tend to not like fractions. There is a way that we can do that's a little simpler. I'll show you that in just a second. Again, to check, we rewrite, substitute, and simplify. Rewrite, substitute, simplify. Let's look back at this real quick. Anything times its multiplicative inverse will give us a 1. There is another way to do this. We could take this 5x equals negative 40, and instead of multiplying by the inverse, we could actually divide by 5. Remember, division is the same as multiplying by the reciprocal. Some people prefer to do it this way because 5 divided by 5 is a 1, negative 40 divided by 5 is a negative 8, and they can avoid writing the fractions off to the side. Sometimes you see those fractions, it tends to mess with your mind a little bit, you freak out a little bit. So some people prefer the division. I don't care which of those you use. I'll tend to alternate back and forth in my videos. Just make sure you understand that division is the same thing as multiplying by the reciprocal. Here's another one for you. X divided by 10 equals negative 70. Now you'll notice down here my Bitmoji just says, yo, I'm in big trouble. This one tends to be one that people struggle with quite a bit because this division writing throws them off somewhat. My suggestion to you is you may find it easier, instead of writing divided by 10, to rewrite this as times 1/10. Remember, dividing is the same as multiplying by the reciprocal, so this would be 1/10 of x equals negative 70. Once I have that, I can use my property of equality and I can do whatever I want to both sides. I'm intentionally going to pick multiplying by 10. Why would I do that? Well, when I perform my computation, 10 times 1/10 equals 1. I've intentionally picked the multiplicative inverse of 1/10. 10 times 1/10 equals 1. I intentionally chose this to get the 1 over here because I know from the property of, from the identity property that multiplying by 1 doesn't do anything. Makes it very easy to come up with the solution. Again, you can check this by rewriting the original problem, plugging in the number you said should work, and then just simplifying to see if the sides match. If they don't match, it means you've done something wrong and you need to go back and rework the problem. Now, it is possible that you could, instead of rewriting this division as multiplying by 1/10, you could just do it as division and then multiply both sides by 10 over 1 up here. You just have to be a little better with fractions that way because you have to realize that 10 times x over 10 is going to cause these 10s to simplify and still leave you with x over 1. There again, you can do it either way. I don't care. Just make sure you're careful. Anything that involves fractions or division is going to be a little more challenging for you. I have one more. This is the last one. You may want to pause the video and try this on your own. Hopefully by now you've figured out how this works. The property of equality says I can do whatever I want as long as I do it on both sides. I want to do something that's going to get rid of this times 3/4. A lot of people say, well, you could divide both sides by 3/4, and that's true, but I think you're going to find it to be a lot easier if you multiply by the reciprocal or the multiplicative inverse. 4/3 times 3/4 is going to give you 12/12, which is 1x when you do your computation. And 18 times 4/3 is 24. Now, I don't really have time to talk about multiplying fractions together. If this is challenging for you, you may want to go back and review that. Just keep in mind that this is the same as 18/1 times, and you multiply the numerators, multiply the denominators. Once again, we chose the multiplicative inverse because we knew that multiplying by 1 doesn't do anything. That's the multiplicative identity. Don't forget to do your check, rewrite, substitute, and simplify to see if they match. If they don't match, you know you've done something incorrect. That's all I have for you today. This does take some practice to get used to. Don't feel bad if you need to go back and re-watch portions of this video once or twice more. This can sometimes be a challenge, but this is the foundational idea for solving equations. Once we have this nailed down, we can deal with equations really of a very large size using this along with the properties we learned in our expression lessons, but we'll get to that just a little bit later. That's all we have for today. Hopefully it made sense for you. I really do appreciate you being here with us, and I wish you all the very, very best of luck. Take care of yourselves. Bye-bye.